you're going to form kinks. If you make the OD small, but your wall thickness too high, then you don't have enough space for the gas to flow back. So it tells you a lot about design constraints that you have to deal with. And the bottom line is, yes, you want a metal that is soft. So we're talking about a low yield strength. But you do need hardening, because if you don't have hardening after you bent it the first time, when you try to come again, that's where it forms a kink. And you know, in terms of the application, you just cannot afford it. So there's a lot of practical joining, material selection, and mechanical properties involved at cold temperature. So some of the materials we were looking at, if they had a ductile to brittle transition at cold temperature, just can't use it. This had to go to minus 100 degrees C. So there are a lot of, it's all practical, but at the same time, you need to be able to go from all you've learned from books and try to apply it to this what is a very, very specific problem. Another example of recent work is these X-ray sources that are in the scanning systems at the airport. This was another project I was contacted because they had trouble. So you have the whole scanning system. You need X-rays. And this device here essentially produces the X-ray for you. It works a little bit like an electron microscope, if you've seen an SEM before, where you start with electrons, you energize them. So the electrons come from that filament here, and they hit the surface, they produce X-rays. And that's what you use to shine on the luggages, and you have detectors on the other side to find out what's going on. So the main objective for these people was trying to get as many X-rays as possible for a low cost. It turns out that the sources of X-ray were a lot cheaper than the detectors. So one of the technologies to improve the scanning systems is to have multiple sources scanning on a single detector. If the detector is 5 times more expensive, and I can sequence it fast enough, if I'm at 600 hertz, for example, in changing from which source the X-rays are coming from, I gain a lot more information about the luggage than if I try to match one source and one detector. The main implication of this is at 600 hertz, this electron current was turning on and off. And I had to tell them, well, maybe you just want to just block it here. So you still have your source running in steady state, and you don't have to worry about fatigue. This was a fatigue issue from the idea of switching the current. The response I had on that is, well, I'm going to need more power supplies. I'm going to need a lot more current. I mean, the whole idea is you have one power supply and you flip it among different sources. And first of all, you don't need to go to a 220 volt or a 480 volt unit. But also in terms of hardware, it's less expensive to put together. So all these practical limitations essentially they tell you that this had to be very hot and cool off at the same frequency of turning it on and off. And that's essentially what we worked on, doing the thermomechanical analysis and trying to figure out materials that would resist potentially higher temperature or higher temperature variations from turning it on and off. So the system, again, you shine here, it's a tungsten type disc. There was a lot of proprietary information that they didn't even tell me about how they made it, but we had to characterize it to the extent we could to know if it will crack or not when it goes through these thermal cycles. So it's just a practical example. It has nothing to do with, in our class, you'll hear a lot about trouble people have. They were sort of okay. They didn't have the life they wanted because eventually they had, and I think I have an image of that. This is the thermal profile on the source, and they had cracks forming on these little tungsten discs where the electrons were coming in. And some of the cracks were transverse, like the ones that are shown here, which may or may not be a problem. If you start with a flat surface and you break it down a little bit in smaller pieces, you can still use it as a source. One of the problems is some of the cracks were bifurcating, and then you lost your thermal conductivity, and you started almost melting the tungsten on the surface because it didn't have the heat pattern to go from tungsten to some form of a copper to a cooling fluid. So this idea of the cracks turning on them was, one of the big issues. And it's not uncommon for materials to have a lower resistance to cracking in the rolling plane, if you will, in the plane where it's formed, because the inclusions get flattened up, and you essentially have pads that of low bonding energy, where you can, if the crack's coming down and it hits a bunch of precipitate or inclusion, it will turn if there are also shear stresses from all that thermal gradient that allows for that to happen. The World Trade Center is something Professor Eager wrote a very nice paper on. I decided to bring it up just to show a little bit sometimes that there's something to be learned from doing these failure analysis. It was a terrible catastrophe, and there's nothing to be do about it. I mean, the building is gone, the people died or were injured, and it's the end of it. There won't be another World Trade Center, although, is it completely up, the Liberty Tower, or are they still working on it? Yeah. Yeah. I worked on the foundation welding. They had issues. It's going to be strong, but when you oversize your design, there are things that normally are not any issues that now all of a sudden you have to worry about it. You put more braces, and now they meet with each other. You have a external expansion trouble if you have redundancy in your system. There's a lot of issues. Anyway, regarding the World Trade Center, one of the issues that came up from looking at some of these photographs, and this is not just my theory. There were a lot of people that have worked on this. Believe it or not, I don't really mind. But from the heat that was localized in a certain area, one of the theory is the wall of the building caved in. And the reason why some people say it caved in is these floor or trusses or joists that, first of all, are very thin metal. They're holding a lot of dead weight, and therefore they will heat up very quickly and sag. So if you have a truss that starts to sag, it pulls on the main columns. It's one of the theories. Now, what does it mean? Well, if you wanted to gain 10, 15 minutes of life on this whole tower, insulate these floor trusses or make them such that they'll come apart and you lose one floor or something, but the whole building, the main columns won't come and starts to buckle, essentially. So it's this idea that, yeah, you want to insulate the metal, and probably you want to insulate the main columns. But if at the end of the day, what ended up being the trigger is this pulling action to create the buckle, then you need to prevent that either by not using steel. You could use concrete, pre-stressed concrete for your floor support, or insulate it or make it such that it will disconnect when it reaches a certain temperature or a certain capacity without creating too much pulling action. So that's, I guess, my one example. If you're going home tonight and say, why these guys do failure analysis? It is just to fight over who made the mistake and that kind of things, and not always. Sometimes it is, sometimes there are lessons to be learned for future design. They changed a lot the fire protection building code based on these studies. Now, blowout preventer, we're not going to have time. I will talk to you guys about blowout preventers. I actually brought a piece right here, and maybe we could do it. I was lucky enough to work on the big spill, the BP. This is a very simple packer system, and what you do, and I'll show in a video, It's a little heavy, but it can be turned around. What happens with these systems is you want to be able to shut the well when there's a drill string in the hole. And there are multiple ways to do that. One of them is to use sort of a donut that will come out of the housing of the well, and press all around against the tubing. Or you can come with two C-shape, which is the design that I'm circulating right now. And it's just a little awesome. I just let it go. It starts over. So this is the whole casing diameter, if you will. So this goes up and down, and what happens is you have the drilling mud or your production coming through that tubing that's inside the well. And this, you're talking about something that's 3/4 of an inch thick, as much as 3/4 of an inch, maybe 3/8 in general. So one of the things that happened with the BP spill is they had some knives to try to get that pipe out of the way, but it wasn't sharp enough at the right location, so they were not able to completely go through that drill string. But you can see that as being a challenge if what you want, it's a valve, okay? But if you want a valve to resist 10,000 psi pressure, which is about 100 times what you have or more, what you have in house plumbing, you need a lot of metal to hold the rubber. So if you look at this here, what we're working on is making a rubber seal between the packer, it's the piece that you have, and the drill string right here. And you also need to make a rubber seal against the cavity around it. It's really not an easy process if there's flow in the well. If you have drilling mud that has all the little particles from drilling, it's very, very abrasive. So there's no doubt that it's a challenging environment to be designing something. At the same time, it is important. If people call it a blowout preventer, they expect that when there's some pressure rise in the well, they'll be able to seal it. It's an example that involves a lot of environmental factor. You can have H2S in some of these wells. So if you have steel, you have to be careful about residual stresses, hardness level. If you have rubber, the rubber also will deteriorate on certain gas environments. So there's a lot of material selection, wear, and just basic design that is involved in this. Now, exactly what was learned, because that's another example of failure analysis, I think a lot of people did learn to some extent that they needed to make not consider these foolproof because they didn't work all the time. So whether they're going to change regulation or whether it still becomes a responsibility of the designer to make these reliable is still an open question, I think, even 2 or 3 years down the road. Because there are some specifications on how to make these, but they're not very detailed. It's a little bit like in automotive. Here's, you need to put the light, and you need to absorb a certain energy if you have an impact, and the rest, good luck to you. There are some performance requirements. They don't necessarily encompass all the conditions that will happen. So that will be it for today. And tomorrow, Professor Eger will start on the welding metallurgy, and I will continue Thursday. And I have this list here about when you make the decision you're going to use structural material, it's more than just putting it on the drawing. So that's what I'm going to talk about on Thursday. It's here.